Hello everyone, my name is Jervan Polman. I'm here to talk to you about how RDF and SPARQL can be used for variation graphs. Now, I'm a developer at the SwissProt group, and I work mostly on www.inpro.org and sparkle.inpro.org. Of course, SwissProt is a strange, different country beyond the mountain where we have a different alphabet and think differently about our information, with those lovely proteins instead of those icky DNA sequences. However, I've been asked to give a small introduction to RDF. RDF is a simple but widely used technology. I only have 20 minutes, so I won't be able to cover every detail, so please do be sure to look at the VG Wiki and ask a lot of questions afterwards. Now, RDF is a very simple way of talking about information. It really is using lots of little simple sentences. Each of these sentences start with a subject, a predicate, and object. These make the direct, the cyclic graph. For example, you could have little sentences like, I love my work. I would be the subject. Love would be the predicate. My work would be my object. Normally I use wife as the object in this sentence, but my wife detests being objectified. However, the key here is you model your information in these simple sentences. You get lots and lots of simple sentences, but the thing is to be explicit about what you know. Now, RDF is a W3C standard. It's a large family of standards with associated things such as validation, conversion, and embedding in other formats. RDF can be queried with SPARQL. SPARQL is a fully standardized semantic query language. It's very much like SQL, so it's a pattern-based graph query language. However, what is really nice is that there's a lot of SPARQL databases. The logos on these slides are the ones which are commercially available. So these are the ones which have real customers, many years in progress, and are really quite interesting. Now, for sparkle.inpro.org, we use Virtuoso Universal Server, which is a very nice, actually, relational column store, which actually does SPARQL as well. It really easily deals with a data set such as Uniprot. For example, you see 3 Oracle logos. That's because Oracle has 3 different implementations of SPARQL standard, each of them with different features and performance trade-offs, but it's a wide segment of the market. Another interesting one is France. And their product called AllegroGraph. It has a very large clinical deployment with more than 4 trillion edges. So all of these are commercial. Gina being Apache project being slightly different. And it really means there is a significant amount of funding behind this project, behind this technology. RDF is different from the other formats you might be thinking about. RDF is a conceptual data format. So that means while you always talk about your triples, how that is actually serialized on the network or onto disk can be extremely different. For example, RDF serializes as in triples, which is really those little sentences you just saw. But you can also embed it into HTML and use it for things like schema.org. Turtle is for a way of showing RDF, which will be shown in the examples that I use, and also many examples on the web. It's very nice because any Turtle file is basically a SPARQL query without variables. JSON-LD is if you have an existing JSON-based API. JSON-LD is a very nice way to bring RDF and your existing infrastructure together. And the same if you have XML. RDF XML is a nice way of doing it. All of these have different benefits and downsides. For example, there's also binary serialization, such as RDF Drift or HTT, which means you have the benefits of binary compression. Key is all of these examples, all of these serializations encode the same information. So you can convert from JSON-LD to RDF XML to RDF-A to N triples. Now, that means that you can change your serialization depending on your use case. But your information and your parsers and your logic don't need to change. Now, RDF is a graph data format. It consists of nodes and edges, and all these are defined as resources, which actually means that all your edges are nodes in their own right. A resource is nothing more than something identified by a URI, or IRI these days, with the expanded character sets, and these are just things like URLs, pointing web pages, QIDs, mail-to addresses, ISBN numbers. Not all of these resolve to web pages. It's nice if they do, but it's not a requirement. Also, some of these URIs will only resolve internally until your local intranet. Some of them never resolve. That is absolutely okay. It's nice if they do, it's not a requirement, and sometimes a legal requirement that they don't. The aim, of course, by identifying things as URIs, which is quite a long string, is that you always have a context about what does this URI really represent to really give a good identification of a resource, so that the identifying part is really done well, so you don't have naming conflicts. At the end of these nodes, sometimes you have literals. Literals are just strings, numbers, and other things that we know as humans how to interpret it, our programmers. For example, this, and all of these use XML data types. You can use your own data types, that's not a problem, but the XML ones are standardized. So you have things like strings, date types, which is basically what you wanted to do for your date types. I always forget what it is, 1807 or 1801 or 1806. And that's associated RFCs. Of course, there's numbers with all the different ranges that you want that's there as well. But very key, there's also the concept of a language string, which is basically associating a set of characters and a known human language, which means that you can have multiple labels for the same concept, but each in a different language, which is why it's very widely used in ontologies where this is very, very useful. Of course, RDF is widely used. Often it's used in the version of OWL because it's a very nice first order logic system. But the nice thing is that OWL and RDF are like two bellies on one, like two hands on one belly, the other way around. And that means that if you have a data source in OWL and you have a data source in RDF, they're automatically compatible. You can cross-query. And many of these data sources that already exist really allow you to do database cross-querying on the user demand without admin intervention. Of course, inside your own alliance, you already use a lot of RDF and OWL, though at the moment it's mostly limited to ontology working groups. But what I really want to emphasize, there's one major difference between the current formats you're looking at and RDF, and that is the magic of community. In Protobuf, XSDs, and XML, and even GFF with its many versions, we always had the problem that one party can evolve the schema. And if two parties try to evolve the schemas, we end up with unfortunate name classes and things don't work. Now, this is better with protocol buffers than it was with GFF, but it remains a one-party evolution of data formats. And that is very tricky in a field where everybody tries to do novel science. That means that we have a lot of standard information, but everybody brings its little piece of uniqueness to the table. That means in historical terms, we have always tried to stuff things into a box so that we can in the end have an existing program draw something. RDF is different. RDF means that if you add information, nobody cares about it, other than in the bandwidth bill. Additive information doesn't break things. And that makes it much easier to explicitly standardize on the small between different bases. And on the other hand, instead of doing minimal information standards, allow everybody to represent the maximum amount of information. And this is a really subtle but strong difference between the RDF and other formats. Now, having discussed a little bit what RDF is, and please do ask questions afterwards, talk a little bit how to model something like a variation graph as RDF. Now, I'll be thinking about the way VG represents variation graphs. I hear from people that there's multiple approaches, but the VG one is very simple and extremely fidel to a way that it would be modeled in RDF. Now I assume that you've seen a VG railroad schema, but basically here we have a linear sequence or two linear sequences with two variants. So there's 4 nodes in total. And in these 4 nodes, I'm going to on the side describe them in the turtle syntax, how they are written down as RDF. And all these little lines are basically triples. But of course, like any time, that would get varied for both. So we want to have some abbreviations. And there's 2 kinds of abbreviations. There's a base abbreviation, which is basically the empty abbreviation, and the prefix abbreviations. So, in this case, the base would be the URI VG schema. We haven't really figured out what that URI should be. Should that be in the GA4GH namespace or somewhere else? There's also a prefix called node, and that's the URI of a VG graph. So we can assume that the different hospitals and different clinical instances have their own variant graphs. They will also, of course, refer to the reference graph, but there will be a duality. Those prefixes allow us to say this node is in our reference graph, and this is a node that is existing in the public reference graph. So here we have 4 nodes. Each time it's node 1, a node. A is a shorthand that is in standard that basically says RDF type of. It's a super useful acronym that is just abbreviation that is used all over the place. We add the DNA sequence as a RDF value. Not just reuse an existing prefix. We could use a more representative predicate, but RDF value suffices. So let's go with that for the moment. So we have those 4 nodes, each with their associated sequences, and that means we have 2 triples per node at the moment. Of course, the nodes are linked to each other, otherwise it wouldn't be very much of a variation graph. For the examples, I've kept it simple, so they're all linked forward to forward stranded. So it's 5', 3'. Just linear as you know it. Node 1 links to node 2 and 3. Links forward to forward, node 2 and node 3. So that's 2 triples. The comma basically means repeat the subject and predicate. Node 2 links to node 4 and node 3 links to node 4. Okay, you can see it on the left, the diagram matches the description in the totals. Concept, of course, that we have to deal with paths. Paths, threads, are basically the linear genomes, the reference genomes, the genes, the things that are currently linear sequences, as you have known from the 1990s or the 1960s, as you might. And these paths can be the genome of a patient, it can be a gene, an exon, anything you might want to annotate. But it's a way that you go through the graph and actually get back a biologically relevant sequence. Paths are really a series of steps. You can model it different ways, but we went for the way to say that steps are their own little piece of knowledge. A step links to a path instead of the path to the step. This has this benefit that if you do a subset of the data, you always end up with a completely valid subset, no matter how small your subset is. So if you only get 1 triple, it's a valid piece of information, even if the total graph is billions of triples. Now I need to show 3 steps here, but slides don't allow for that. So step links a node, a rank, and a path. If you think of steps and ranks as the rank in an array of steps, then you get the right order. You need to have a link a step and its path because you will have many paths in a single variation graph. That means you need to be able to associate these 2 points. And you need to do so explicitly, otherwise you will have problems with your queries. So you can't have any implicit information. You have to make it explicit. Using implicit information is fine for serializing it to disk, but if you want to expose it to external parties, you have to make everything explicit. Variation graphs can be explored using SPARQL. SPARQL is just a standardized query language. It looks pretty much like SQL and is pattern based. In this query, I'm just going to go through it And we're going to build a FASTA from a VG file, from a VG graph. So we use an existing prefix, VG, examples, and RDF, standard one. So the first part, of course, is the select clause. So here we're looking for a path, and then the sequence associated with the path. And we're using the group concatenation operator. We don't want to separate it there because you're basically making a little IUPAC DNA sequence, and spaces in it are annoying. Select is not the only option for SPARQL queries. You can also have ask, construct, and describe. Construct makes RDF, select makes tab delimited, ask is boolean, true, false. Describe is for navigating data quickly. It's not standardized in its output, but it's used for discovering data sets. All of these are followed by a where clause. And here we're basically asking for something. We don't care what, so we give a blank node. Path that has also a node and a rank. And for the node, we actually want associated sequence. Here you see a lot of implicit joins. That doesn't mean that your database underneath is actually doing joins, but it does mean that joins are implicit, unlike in SQL, where you have to do explicit joins. Wherever a variable is shared, it's a join. We want to group by the paths so that we get a different sequence for every one of the paths, and we order by a rank to make sure that the concatenated sequence gives back the right order. If you leave that out, we have a problem. You can do similar things in SQLite and Postgres. It's a standardized, also in SQL you have group concat, although different databases use different terminology for it, which makes it quite different for SPARQL, because SPARQL is a standard query language, and it's a very small query language compared to SQL. If you have ever seen the latest SQL standards, that's a good bookshelf. SPARQL, though, you can read through in a half an afternoon and understand, well, everything except maybe some of the subtleties. For more queries, do have a look at the VG wiki. There's a lot of interesting queries. Also a few which don't use completely standardized SPARQL, but are nice for graph traversals. Now you'll be talking about, will this actually work? Will this scale to what we need for variation graphs? Now, we have done a small experiment with the VG1000 genomes. Eric Garrison probably has explained this before, how he did it, how he built it with VG, and I can translate it to RDF and loaded it into Virtuoso 7. That actually only means one VG1000 genomes, the variation graph, is 50 gigabytes on disk in an existing database. That is today. Nothing's fantastic about that. There's a lot of optimization that are possible, but those haven't been done. So it could be much less. VG1000 genomes, I did some napkin math, and that shouldn't be more than 2 terabytes on disk in an existing database. And considering how much it costs to gather 100,000 genomes, 2 terabytes on disk is well within reasonable, available, and affordable capacity. Now, to summarize, I would like to say RDF is a simple data model that has consistent identifiers, and crucially, anyone can say anything about anything. There's an associated query language, and it's for graphs. It has a wide-scale commercial deployment. It might not be hyped, but there's large-scale deployments. It comes with a HTTP REST interface. It is in clinical use, and really nicely is there's federated queries. That means that on demand, when allowed, you can combine any 2 SPARQL endpoints over HTTP as if you were one. This of course has lots of issues associated with federated querying, but it is really powerful for doing quick demos and seeing if data is worth integrating at all. Last but not least, SPARQL can be used for doing variation graphs, not for building them, but for querying them, for having them running long-term inside hospitals. Hospitals don't really like PhD-written software without any kind of security or clinical legal testing to them. Oracle and others have done that and are therefore today deployable inside a clinical setting. So thank you for your time. I would love to hear your questions. Do also send them by email. This work wouldn't have been possible without kind support of my management at the SIB. But at the same time, it would not have happened without the kind support of the DBCLES and NBDC in Japan for hosting both the RDF summits and the long-term biohackathon series. Of course, adding RDF to VG would not have been possible without Eric Garrison and the rest of the very, very welcoming VG team. So once again, thank you for your time, and I hope to get your questions.